come back to part 2 of my AI series. So since the last time I just added a few more assert statements, and I think we will do one more thing, which is implement chain reactions before we do our first commit. It's already a big commit, but whatever. So just to show you again, the last test that we made is okay. It doesn't wrap around the corners. Nothing unexpected happens. I actually thought maybe I'm gonna abuse this test to immediately test more than that. One second, what happened here? Board value at 10132. 10 is not. This one fails now because we changed the board. So while falling over, we can see. How to explain? What I just did is I moved the red block from the corner right next to the green block, and now when it falls over, it falls on top of the red block. So now we have 5 green ones there. One thing we can see is it already works that if our box falls onto an enemy box, it changes the color. But we we now need to implement chain reactions. So what happens next? For this, I would probably see do I wrap this in a function, or do I how do I implement it? So for now, I think one thing we can do is we wrap all of this function in a function. X, Y. So we want to throw over X and Y. And one small addition that I want to make here is I want to subtract 4 instead of setting it to 1, because when you get chain reaction, you can imagine a situation where you would get more than 5 on a particular field in one throw. So one thing I can do now is throw X and Y, and the test should still work. 2 positional arguments. I need to provide self as an argument here. Okay, this still works, but the test still fails because the chain reaction is not yet implemented. So what do we do now? We make an additional function which gives us if there's any field bigger than 5. Just take self for row and for column and self in row, which let's call it field to be consistent. The way chaining is gonna work is we will throw over all fields on one board, and we're gonna throw over all fields on a board. This might create new stacks of 5 boxes, then we're gonna throw all of them over, and then again and again. So it's I think this is gonna be most natural. Because another thing we could do is we go through the board. If we find a 5, we throw it over, and then we start again from the beginning, which would always throw the most top left 5 first. Yeah. So X, okay. Yeah. Return fields. So this one should be tested, maybe. But maybe it's fine for now. Let's just see. Okay, it's see. Okay, this one finds as field 1, 0. So maybe you can see it here. So this is still the assert that's failing. We assert that this column should be a 1. This field should be a 1, but it's a 5 now. And our function returns now 1, 0 as a field that we expect to be thrown over next. It's equals 1 fields. Throw over. This should work. You can just copy this line. Okay, what's happening now is we get all the fields that we need to chain. And then if we have any fields, we go in here, and for every field we throw this field over. The star in this function parameter just means that since it's a tuple, we will unpack it into the arguments. And after that, we check again if we have anything to throw over. And as you can see, the board changed. So first we threw over the corner. The corner threw on the middle, which then again fell over again, throwing 1 box back. So this is actually what we expect. And the assertion that's failing is now saying that a value 0, 0 should be 1. So actually in this example, what we expect is when we throw the top left corner over is that due to a chain reaction, we get something like this. And then value equals 4. This one is 0, 0. Well, it's actually 1 and 1 because we have to generate. Yeah, okay. So one fun thing to try now is what happens if we throw over a board that is full of stacks of 4. Here's 1, here's 2, here's 2, here's 2, here's 1. Let's just assume this. Yeah. Bam. One quick second, we need to remove the print from the test, otherwise it is confusing. Okay. Bam. Is it easy to say why this happens? Not at all. It used to be all 5s before, and then let's see. One fun thing is, if this is a 0, this is some of the patterns that I hope we could find later on. Let's just say we have this has to be a 3 of 2, 0, 0, 0, 0, 0, 0, something like this. Imagine a state like this. So green managed to make a couple of 4s around a block of 3 of blue, but this stack of 4 is not approachable from either side. If red places here, blue could throw this over. And beat you. Blue would always be the winner. But in this particular case, if now red throws over the corner right 4, it would throw over the right 4 next to it and the 4 to the bottom, which in case both would make the middle field become 5. Yeah, maybe I'm not explaining it easily. Let's just see how it goes. First clear the screen, and then we do this. I didn't save. Yeah, everything is full of. This is basically the winning move. So here it's easier to see. So if now green puts a stone in a stone box in the bottom left corner, and this will fall over, it will throw over the fields next to it, the top 4 and the bottom 4, which will both have a box that falls into the middle field, which will add it to 4 and eventually 5, which will make it fall over and make this 4 fall over, and yeah, so the whole field is green now. Chain reaction, def, all, test, something like that. Let's make this a test where we afterwards assume so insert here we would assert that 2 evaluate 2 should equal 4, and the player and 2 should equal 1 after this. Please think from I also see maybe inconsistency here. So let's stick with what I did before for my tests. Big follower. Okay. Syntax error. I'm trying to assign things. Okay, nice. Okay. So this kind of took half of the episode, but now one more thing which would be a winning condition is one win. How do we do this? In row for row instead of pair. If they are all one, return. Return 2. Here we can also assert winning player equals 1. Row is not defined. No, it's like this way around, isn't it? Yeah. Okay, now we can see who's winning. Now we can throw our stuff. Time to commit our board. Git pi. Okay, this is now in the repository. Next, what we're gonna do is we will probably start with an easy AI. Max pi. So this will be our MinMax AI. And what we need is actually we're probably immediately gonna implement more advanced version. You first have to look up it's called Nigga Scout. The way Nigga Scout works is it's a tuned version of alpha beta search. Let me see. Is this the one we want? I kind of remember this is the one. Yeah, maybe we're gonna do it step by step. So let's first MinMax it maybe, and then improve our approach from there. We have a class MinMax, and what the class needs is just move, and it takes no state actually. And it takes a board as an input. And let me think how to do this best. Okay. So the board needs to somehow give me all moves. It needs to give me all available moves. And then I do from, I will basically play every move. So here we would have played this move, and then we want to maximize this board position, and then you may ask, why do I make two functions now? This will become clear a bit later. First, we're gonna maximize this particular position score equals, so yeah, and then maximize board depth. Let's say we're gonna go depth 3 from that. Not sure the board should know anything about its score. Board. Something, this is a little bit pseudocode now, but maybe it should be something like this. Boxes for something like this, minus board is for board the player, something like this. So maximize score is minus board. Board undo last move, next score bigger, best score. Something like this. So okay, we go through all the moves, we do the move, we then minimize this current board, and then when we return, that's the -1. When we return from that, we undo the current move, we check if the score that we found is now better than our current best score, and then we return best move. So, and in minimize, we would do the same thing. Just to write it out, you can see that it is basically copy and paste. Yeah, no, this is stupid. So this is basically go in here. So here we can call maximize again. Even though this player is trying to minimize, we take the negative of what this returns. So we are trying to, in this function, we're trying to maximize the score. If we say, just give me the maximum score right now, we get it back. If we say, give me the score that we get at depth 1, we find the smallest negative score, which is the biggest score that we can reach. So this pseudocode should work. A couple of things that we need to implement in our board in order to make this work is box is 4, and this one will be a player. And here we do some num for x in row 4, row in. Maybe I should make this a loop, otherwise it's. We want to sum up all the fields that are belonging to the player passed to this function. So and I'm a little bit too lazy to make it in for loop, but maybe this hurts readability a lot. So okay, let's make it 0 for row x. I forgot to enumerate there, and I forgot to here. If now say player x field. So okay, we go through the whole board. We see if the player at the field is the player that was passed to the function, and then we return the number of boxes. So let's copy this function and make a test for this. Test. We can just leave this and just boxes for player 1 should equal 4, 8, 12, and forward boxes for player 2 should equal 6, 10. So and then we need to add this test. This boxes 4 and test big. Big for logo. Whoop. I test. Okay, this passes. Okay. Wow, time is flying. So the next thing we need to add for our MinMax to actually work is we need to get all available moves, and we need to undo moves, and we need other player. This is something I'm still gonna do. We're gonna make this a property if this needs to change slightly if we have multiple players. Should keep that in mind. And then current player. Again, other player. Service notified. Board. It's getting late. Okay. Still works. So we can kind of assume that other player works. This means this line in our MinMax function works. I want to rename this. Actually, this should be an internal function for this class. self MinMax. Okay. Okay, this episode is getting long. In the next episode, we need to implement get available moves, and we need to implement the undo. And then I think this should work. I'm also gonna look again into this one. So one thing I want to implement is something I remember as Nigger Scout, but it's actually also called principal variation search. MinMax is the correct one. They're all very similar. So, but what's happening here and what we're gonna do, but also the difference. So what we're gonna do is we're gonna implement a principal variation search slightly differently, and I remembered it to be MinMax or one of these, where okay, we have one function that calls itself in a negative manner. We're gonna add alpha beta windows because cutoffs are essential, although I think initially this might not help too much because everything's gonna look similar, but we're gonna understand this as well. The difference to how the code is written here is principal variation search assumes that we already know what a good move might be, and then we do this move first and hope that we get very restrictive alpha beta windows. Also in the next episode I might explain a bit more how alpha beta search works and why it's better than MinMax, and yeah, thank you for watching and stay tuned.